When the moon forms, it is just 17,000 miles away, but it doesn't stay as close as that. Its violent birth sets it spinning away from us on a journey that will last for 10 billion years. Absolute proof that the moon is moving away comes in 1969, when astronauts leave an 18-inch reflective plate on the moon's surface. By bouncing lasers off this plate, scientists can pinpoint the moon's distance from Earth to within an inch. Such calculations reveal that the moon is moving away from Earth at a rate of about 1.5 inches per year. So why is the moon on the move? In the 1990s, supercomputers gave scientists a more accurate picture of what happened 4.5 billion years ago. Computer models of the creation impact reveal that the collision of Theia and Earth is a glancing blow. It imparts a rotational force to the Earth. This rotation gives Earth its days and nights. But the huge power of the collision sets the Earth spinning far faster than the moon, which orbits around it. In these early days, Earth spins once every 6 hours, 4 times faster than today, whereas the moon takes 20 days to complete one orbit. So the moon orbits more slowly than the Earth spins. However, the early moon is 15 times closer than today, which makes the effect of its gravity so strong that, as this graphic demonstrates, it pulls up a bulge on the Earth's surface directly below it. This bulge moves like a tide across the Earth's surface with its own gravity tugging on the moon. Because the Earth spins faster than its satellite, the bulge is always ahead of the moon. So it constantly pulls the moon forward, causing it to accelerate. Any object that travels in a circular motion will move outwards as it accelerates, much like a hammer being thrown in the Olympics. As the moon accelerates in its orbit, it starts to spiral away from Earth. It's a journey that will continue for billions of years. At the time of its birth, the moon orbits Earth 15 times more closely than today. But this close proximity puts the moon in great jeopardy. It faces a bombardment by thousands of asteroids, which will destroy 80% of its surface. It is now 4 billion years ago, a time the scientists call 4 giga-years ago, or GYA. The moon now orbits 86,000 miles away, still 3 times closer to the Earth than it is today. From our planet, the moon dwarfs everything in the sky. During this early period of its life, the moon has its most profound effects on Earth. The massive collision that creates the moon is so powerful that it knocks the Earth off balance onto an axis of 23.5 degrees. It's this tilt that gives us our spring, summer, fall, and winter. If we spun on a vertical axis, like the planet Mercury, seasons would not exist. Everywhere would receive 12 hours of light and 12 hours of darkness. The poles would be entombed in an eternal freezing twilight, while the equator would bake in endless heat. But the moon does more than merely produce this tilt. It also maintains it. The strong gravitational pull of our young moon acts as a global gyroscope, stabilizing the Earth's axis. Astrobiologist Lynn Rothschild explains.
The reason we have this obliquity that holds steady is because the moon helps to stabilize the obliquity of the Earth. If we had no moon, we would end up with what the astronomers call a chaotic obliquity. We'd have quite a big shift and fairly low time scales.
Without our global stabilizer, our axis could vary between 0 and 90 degrees. This would alter the distribution of sunlight across the surface of the planet, devastating our finely balanced weather systems. Climate patterns would go berserk. The tropics could find themselves frozen under ice, and Antarctica transformed into a vast desert. But luckily, the moon saves us from such disasters and allows life to exist.
It turns out that it may have had a really profound influence on how life has originated and evolved on the Earth. In fact, you might almost be able to argue that we wouldn't be here today filming this if the moon weren't up in the sky.
Not all planets in our solar system are so lucky. Mars has 2 moons, but they are too small to stabilize its tilt. As a result, the red planet rolls much more than Earth. Some scientists believe that this is one of the reasons that there is no life there now. When you look at our moon today, the first things you notice are the craters. They tell astrophysicists, such as David Kring, about a distant and violent past.
You can look up from your own backyard and see impact craters on the lunar surface. There are over 300,000 craters, half a mile to over 500 miles in diameter on the lunar surface.
Most of these craters come from meteorites hitting the moon. The largest crater you can see from our planet is the Imbrium Basin. It is 700 miles across. Moon craters come in various sizes, but almost all were created at around the same time. Around 4 billion years ago, a chance alignment of the gas giants Jupiter and Saturn changes the shape of their orbits. This creates a slingshot effect, hurling asteroids toward the inner solar system, straight at Earth and the young moon. For millions of years, asteroids bombard the entire inner solar system.
Some of these impact events would have produced impact craters the size of continents or larger. These type of impact events have the capacity to obliterate any oceans on the surface of the planet and superheat the atmospheres. Life as we know it could not persist on the surface of the Earth.
This period of intense bombardment is called the lunar cataclysm. The Earth's gravity makes it worse, pulling meteorites and asteroids directly toward itself. On its own, the tiny moon might have escaped with less damage, but it's too close to Earth. Asteroids heading for impact with Earth hit the moon instead. The moon becomes the first victim of collateral damage. Most of the craters on the moon formed during the lunar cataclysm. 80% of the lunar surface is destroyed. Molten basalt oozes from fissures and fills impact craters, creating seas of lava. Over millions of years, these will cool, solidify, and turn into maria, or seas, such as the Sea of Tranquility. It is the pattern of dark basalt rock that creates the face of the man in the moon, as we know it today. David Kring demonstrates exactly what happens to the surface of the moon when a meteorite strikes. He releases a 5-pound rock from 50 feet above a sand pit. On impact, sand is fired upwards into the air. During the lunar cataclysm, some impacts are so big that material fired upwards